Hey, so there's 5 questions out of 20 on your exam that cover this particular topic. So I wanted to make sure that we went over it before you took your exam. So imagine this drawing is a map, and each of these things are streets, and each of these little squares are buildings, or rectangles are buildings. And you're a mail person, and you have to deliver mail to each of the buildings that are shown in the picture. You'd like to be able to park your car and walk to deliver the mail to each of your buildings. But then you want to end up back at your car without doubling up any streets. So without like going down the street, like going this way on the street twice or going this way on the street twice. So you want to be able to do each side of the street one time, and that's it. Is it possible to do that? So pause for a minute, take a look at the picture, decide, do you think it's possible that you could, say, park your car up here and walk to deliver all the mail, going up or down one side of the street only one time? All right. So we're going to come back to this question because I have a very easy way for you to figure this out. So what we're talking about is something called an Euler path. And this Euler guy, he was very, very busy because when we talked about exponential functions and the letter E in exponential functions, that was Euler too. But we're talking about something called Euler paths. And so there's a few vocabulary words we need to get down before we talk about them. And these are going to help you solve that mailman problem. So when we talk about an edge, we mean pieces that are connected by vertices. So for example, from A to B is an edge. From B to C is an edge. From D to C is an edge. If we come down here to this drawing, this little circle is actually an edge. A vertex is just the point that connects the edges. So there's a bunch of vertices, but C is a vertex, G is a vertex. This little point right here that I haven't given a name to, that's a vertex. A loop is a special edge with both ends attached to the same vertex. So this little circle right here is a loop because it goes around and it begins and ends at the same vertex. And then the degree is the really important part. The degree is the number of edges attached to a vertex. Loops count as 2 edges. So for example, I'm actually going to write down the degrees of each one of these things. So I'm going to write down the degrees first. So A has 1, 2, 3, 4 vertex or edges going into that vertex. B has 1, 2. C has 4. D has 2. F has 4. E has 2, and G has 2. Okay, so to be considered an Euler path, a couple of things have to happen. You need to be able to go over each edge only once, and you have to go over every edge. Also, you will know that this is possible because at most, you have 2 vertices with odd degrees. So if you look at this one, all of the degrees are even, which means this is an Euler path. There are no odd degrees. So I should be able to, if I choose the right places to start and finish, I should be able to go over this whole shape, only going over each edge once and going over every edge. So if I go down this way, I can go from A to E, and I'm going to write that down because that's how we describe these paths, is in the order of the vertices that we touch. So then I'm going to go E to F, F to G, G to C, I go C to B, I go B to A, and now I can go A to D, D to C, C to F, and F back up here to A. So I was able to trace this entire shape by going over each edge only one time, going over every edge. Now notice that I touched certain vertices more than once, like C. Notice that shows up twice in here. A shows up 3 times. F shows up a couple of times. That's okay. As long as I've only covered each edge once, then that's fine. So here's another example of an Euler path. And I want to test this out real quick. This vertex has a degree of 2. This one has a degree of 4. This one has a degree of 4. This has a degree of 4. And each of these have a degree of 3. So in this case, I do have a couple of odd vertices, but it says I can have at most 2 vertices with odd degrees, and that's all I have is 2. So I should be okay to do this one. So I have to get my note out because I mess this up every time. Okay, so if I go from F to B, and then I go B to C, and then I go C to F, and then I go F to E, and I go from E back up here to B, and then B to A to C, and C to E. Now that one was tough. I want to show you how many times I had to find that path. These are all my attempts to find the path that would go around that shape. So I'm not saying it's easy to find a path, but I'm saying that you can tell whether it's worth trying by looking at how many degrees are in each vertex. So now getting back to our mail delivery question, what we really want to look at is an Euler circuit, because remember, we wanted to start and end at the car. So we want to start and end at the same place. And that's what makes it a circuit, is that it starts and ends at the same vertex. So I'm going to label my vertices here, A, B, C, and D. But in order to be a circuit, there can be no odd vertices. So 1, 2, so A has 2. Remember, a loop counts as 2. So there's 1, 2, 3, 4. Down here would be 1, 2, 3, 4. And here would be 2. So I know I have all even degrees. So that means that I can, this is a circuit. So all even. So now it's just a matter of figuring out where to start. Now this is a relatively easy one. I could actually start at a bunch of different places, but I'm going to start here at C, and the first thing I'm going to do is I'm going to go around the loop. So I went from C to C, and then I'm going to go down here to D. I'm going to go around the loop, back to D. Then I'm going to go over here to B, up here to A, and then over to C. Okay, so now let's see how we would apply this to our mail delivery question. Okay, so remember, an Euler circuit starts and ends at the same vertex, can have no odd vertices. All right. So let's say we want to park our car here. Okay, we want to park our car here. We want to get out and deliver mail. So let's call each intersection a vertex. And we don't have to go beyond the end of those streets, but we do have to get down here to the end of the street. Now, the thing about this is each street technically has two paths. We can go down one side, up the other side, or we can go down this side, up the other one. So we have some options for the way that we travel. So whichever direction you choose to go, let's call this side of the street one path. And this side of the street is another path. Now we know we would go like this and down, but just for the sake of making this a little easier, we'll make the paths look like loops. So each of these streets has a loop that looks like this. Okay. Oops. Okay, now what about the middle streets? Well, to get up this street, we'd have to go this way and then this way. And then we would walk along that building, and we could walk along that building that way. And then this one, we could go from here to here, or we could go from there to there. It doesn't really matter. We have to decide which way we have to go. Same thing here, and same thing here. So the first thing we want to know is this possible? Okay, we have all of our paths covered. We want to know, is it even possible to walk our whole path, or all of the paths, cover each side of the streets that we're responsible for, and end back up at the car? Well, remember, the Euler circuit has all even degrees. So let's first check the degrees to see if it's even possible to try to map out a route. So this vertex has a degree of 2. This one has a degree of 2. Looks like all the outside ones are going to have a degree of 2. The inside ones, they have all these different paths intersecting. So this is 2, 4, 6, 8. That one's going to be 8 as well. So is that one, and so is that one. So all of our degrees are even. So yes, it is possible to walk this entire path and end back up in the same place where you started. So let's see how that would be possible. All right, so if I am the mail delivery person and I start at my car, I can go this path to this one. Kind of do the outside parts first. Go around this way. Okay, I definitely have to get from this street over here, so I'm going to go this way and go up and around. I'm going to go this way. Kind of seems like we sort of do the outer edge first. Okay, so I've covered all of these paths. Now I can go this way and here. Okay, now I don't want to go back to the car yet because I still have all these inside paths to do. So I'm going to go, I could really kind of go any direction I wanted. I could go up here and around and back. I could go this way and around. So, you know, maybe it depends on what time of day it is. Maybe there's lunch over here I really want to get or something, but here's one possible path. Go around the building. And then my last path is the one that takes me back to my car. See, so a very kind of simple concept to help us map out something that was really kind of complicated. Even just seeing if you were able to cover all of this area and still stay parked in the same space. All right, so here's another what if kind of situation for you. In this situation, you're planning a bus route. So stop A is the bus garage. So this is going to be where you start. Stop E is the school. So this is going to be the end. The rest of the points are bus stops. So you need to figure out a route that will get you from the garage to the school without missing any stops and without driving over any roads twice. Okay, so pause for a minute, see if you can figure out how you might do that. Okay, so we're going to come back to the bus situation because this scenario is we're looking for something called a Hamilton path. Now, Hamilton paths are, kind of like Euler paths because they have edges and vertices, and you're trying not to duplicate certain things, but in a Hamilton path, we care about the vertices. We want to use every vertex once. We don't really care about the edges. We don't have to use every edge. You could retrace an edge if you wanted, but you don't have to use every edge. It's the vertexes that matter, the vertices that matter. So here's a pretty complicated looking path. I want to make sure that I hit every vertex on this path. So I'm going to go from A to G, from G to F, I'm going to go from F to E. There's actually multiple ways we could do this. E to D. I'm going to go up D to C. C to B. And B to H. Okay, notice I didn't necessarily have to start or stop in the same place that I started, but I did hit every vertex. Now, unlike Euler paths, there's not a rule that says, yes, you'll have a Hamilton path, no, you won't. You just kind of have to try it. And then to be a circuit, which also sometimes is called a cycle, it just has to come back around and start at the same place that it ended. So if we had instead, let's say from point C, let's say we did everything the same. So we did A, G, F, E, D, C. But after C, let's say we went to H, then to B, and then we went back to A. That would give us a Hamilton circuit, not just a Hamilton path. All right, so let's go back to our bus path problem and see how this might apply. So what I'm really looking for here is a Hamilton path, a path that will take me through each of the vertices and will start at the bus garage and end at the school. So if I go from A to D, and then from D to F, and then I go F to G, G to B, B to C, and then C to E, I have my Hamilton path. I haven't duplicated any streets. I have hit every bus stop. I started at the bus garage and I ended at the school. Now, if I wanted to make this a Hamilton circuit, I would just have to get from the school back to the bus garage without duplicating any vertices. And really, from the school I could go down this way, but I would hit G again. Could go that way, but I would hit C again. So I don't really have a Hamilton circuit that I can do here, but there is a pretty simple path back to the bus garage. So mostly what we're looking for is just to make sure that to make the bus trip as quick and as efficient as possible, we don't duplicate any roads unnecessarily, and that we get to every single bus stop, which we did with a Hamilton path. All right, so for your test, you need to be able to read these strings of letters and follow them around a shape. You need to be able to determine if something is a Hamilton path. You also need to be able to determine if something is an Euler path or an Euler circuit. You need to be able to determine if something is an Euler path or an Euler circuit. So you definitely need to know about the degrees and vertices. And then you also need to be able to identify loops. So make sure you know what loops are. Okay, good luck on your exam. Bye, guys.